Gauss's law deals with electrostatic flux and electric field. Okay, the flux through a closed surface, if that closed surface closes a charge Q, is going to be 4 pi kq. Note that's also sometimes written as Q over epsilon naught, where epsilon naught equals 1 over 4 pi k. 4 pi k and epsilon naught are reciprocal quantities. For some purposes, epsilon naught is better notation. For some, the k notation is better. I tend to use the k notation. But it's kind of 6 of one, half dozen of another. Some texts do one, some texts do the other. One advantage to k is it's a lot easier to remember. 9 times 10 to the 9th Newton meter squared per Coulomb squared. Epsilon naught, I don't even remember what it is, but it's 1 over 4 pi times what I just said about k. Now, point charge, for a point charge or a spherically symmetric distribution centered at a point P, we see that the field on the surface of a sphere centered at P has to be uniform. That is, we have the center of a sphere and the outside of the sphere. Every point on the sphere is at the same distance from the center, so that the field due to the charge at the center has the same magnitude, and the field is coming out straight out from the charge, and the radial line is perpendicular everywhere to the surface of the sphere. And that also holds if you have a charge distribution that's spherically symmetric about the center. Now, the field on the surface of the sphere is therefore going to be total flux divided by the area of the sphere. Since the flux is the area of the sphere times the electric field is flux over the area. And of course that comes out just kq over r squared. And let's see what we said here. Q is a total charge inside the sphere. This doesn't hold just for a point charge at the center. This holds for any spherically symmetric distribution. Okay? All the charge inside the sphere, you add that up, and you calculate your electric field based on all that charge, where r, of course, is the radius of the sphere. If you have a long line charge of density lambda, you put a cylindrical surface around some length L of that distribution, and that length L and that cylinder will therefore enclose a charge that's equal to lambda times L. The flux through the cylinder is therefore going to be 4 pi k cubed, which is 4 pi k times the lambda L. The area, the curved surface here, is 2 pi r L. We've seen, and we've gone over the idea before, that the electric field comes out of this line charge, this long line charge, in a radial direction, like bristles on a brush perpendicular to the handle, and cuts only the curved surface. So this entire flux exits through the curved surface, which has area 2 pi r times L. The electric field is therefore flux over area, which comes out to be 2k lambda over r. Now notice that for spherically symmetric distribution, we had an r squared in the denominator. For a long line charge, we just have an r, first power, in the denominator. And note also that I've maybe drawn this a little carelessly. This thing should really extend. We don't want this to look like this cylinder is close to the end of the line charge. This cylinder is far from the end of the line charge, so that what we said about the symmetry of the situation applies, and the electric field comes out of the cylinder perpendicular to the axis. Again, we've gone over that in much greater detail. I'm just trying to refresh your memory on this, but those are the ideas that we need to use. And we also have seen that for a large plane with a charge density sigma, if we have a cross-sectional area A in here, we can draw this perpendicular box that goes through the surface with uniform cross-sectional area A, nice rectangular parallelepiped, a rectangular box. The ends also each have area A. By the symmetry of the situation, the only direction that the field can have is directly away from or directly toward the plane, so that the flux out of the ends of the plane, the flux comes out of the ends of the plane, and the ends of the plane, the flux comes out of the ends of the box. The ends of the box have total area 2A. Again, since the flux is perpendicular to the plane, it comes out the ends of the box, not the sides, so it all comes out through an area of 2A. Now the flux is therefore 4 pi k times the enclosed charge. The enclosed charge is the charge that just sits on this area A where the box penetrates the plane. And that charge, if the charge density is sigma, is going to be sigma times A. So the 4 pi k cubed is 4 pi k sigma A. Total area the flux comes out of is 2A, so that the electric field is flux divided by area. Comes out to be 2 pi k sigma, and there's no dependence on distance. So that as long as you're much closer to the plane than you are to the edges of the plane, this symmetry argument that tells us that the field comes out perpendicular to the plane holds, and this whole development, this whole derivation of this electric field then holds, and we have electric field as 2 pi k sigma.